about today is, now that we've kind of talked about heat balance, we're going to talk a little bit about acute responses to this heat stress. Try to get you caught up with folks in class here. I haven't had a chance to tape one of these in a few days. So the main thing when we're talking about the body, we know that it has a particular core temperature range that is very important. It's usually about 37 plus or minus a degree Celsius. Again, above 41 to below 35, those are going to be where we start talking about life-threatening temperature with the core. And again, this is going to be a number of different influences on this. Really, for a lot of what we do, humans are not just physiologic temperature regulation. We do a lot of behavioral regulation as well. Clothing, moving our bodies to an area where it's not as hot, using air conditioners, fans, altering humidity. These are all things that behaviorally we've been able to do and to help kind of modify our environment. With physiologic temperature regulation, this is where if we start talking about being in a hot environment or exercising in a hot environment, we really have to do one of a couple things here. Either regulating the heat production or dealing with heat dissipation, depending on what we have going on. And this is where we have a lot of thermoregulators, things like receptors, kind of doing that perception, and then we have these different effectors that we can use to either come up with ways to metabolically increase heat production or decrease it, and ways to either dissipate it or gain heat. And again, this all kind of goes back to this idea, back to that original equation we've been talking about, but now we're talking about when you get into a hot environment right away, what happens, not just necessarily here's the heat balance equation, but we have a number of things that are going to influence our heat gain as well as our heat loss. And these are all going back to stuff that we talked about with the heat balance equation. Metabolic heat obviously is one of these. Just normal being alive, you're going to generate heat. Anything you're doing more active, such as exercising, you're going to be generating more heat. And as I said a number of times, with a lot of those environmental factors that were part of the heat balance equation, given the right conditions, conduction, convection, and radiation can all actually be heat gains. Really, with heat loss, it's those four things as well. Conduction, convection, and radiation can be heat losses. Again, that's going to depend a lot on environmental conditions. The other one that's going to play a role, and probably the biggest role in especially high heat, is evaporation and using that ability to sweat and dissipate heat that way. So again, it's those factors such as heat production, our age, our weight, our body shape, all these things are going to play a role in how we generate heat, how much heat we are able to dissipate. We can have a number of different things that modulate that as well. What is the temperature outside on a particular day? Is it humid? Is it windy? Do we have enough water in us to be able to sweat without worrying about dehydration? Have we acclimated to this environment or not? These are all things that are going to play a role in whether or not we're going to have increasing body core temperature or get to hyperthermia. And again, it's that heat index, that what does it actually feel like? What is the thermal load of the environment, not just what is the actual temperature is all. Again, our mechanisms of thermoregulation are really our different body systems here with sweating and blood flow, as well as shivering and blood flow. Granted, we're talking about hot environments, so that is not going to be as big of an issue with how do we generate heat. But what we're going to see is there's some actual skin temperature and some actual core temperature that is going to generate a threshold. Whether or not we start doing heat dissipation mechanisms is usually going to be dependent upon that core temperature. But really, a lot of times we're looking at the difference between the shell or skin temperature and that core temperature. If you have a hotter skin temperature, it's going to mean a lower core temperature is necessary to bring about some type of thermoregulatory mechanism. So again, it's a combination of core and skin temperature, and at any given skin temperature, proportion of the core temperature is going to trigger some effect possibly. But again, the higher the skin temperature is, generally means that the core temperature necessary to bring about those heat dissipation mechanisms will be lower the hotter the skin temperature gets. This is part of the reason on a cold day when your skin's staying nice and cold, you might not sweat as much if you go out and run, or if you're out on a high humidity 90-degree day, it doesn't take much time for you to start having trying to dissipate a bunch of heat, and it's mainly because your skin temperature was already quite a bit higher. And again, this core temperature is going to be dependent upon how much metabolism we're doing, how much metabolic work we're doing in terms of muscle flow, muscle movements. It's also going to be a combination of that, along with where's the blood flowing to, where's it flowing from, is it being able to bring heat with it or dissipate heat, and also, again, that difference between the core and the shell. Do we have conductive mechanisms where we can dissipate heat off that core? Is there a good gradient, or are we warm all over so there's not that gradient to move this heat around? Skin temperature, like I said, ends up being important on this. Ends up being a big deal, mainly because that skin temperature is going to be somewhat predictive of core temperature, and it also is kind of giving us an idea of how much heat storage we are in for. If, like I said, if they are closer to the skin temperature is closer to the core temperature, that means it's not going to take much of a temperature increase to be in a kind of more of a heat storage type of state, which is what we don't want. And this allows us to be able to calculate, or the body to calculate, what type of responses we need to dissipate this heat. Can we do sensible heat loss in terms of that radiation and convection, or do we need to start maybe an evaporative cooling mechanism in order to dissipate this heat enough so we do not take on a big positive heat storage? And again, at rest, most of our heat is coming from just normal body function. It really gets increased quite a bit when we start doing any type of exercise. So during even moderately intense exercise, there is going to be a large fold increase of metabolic heat being generated. Tends to be at the very slow ends and the very high ends of movement, we tend to be less efficient, and because of that, we are going to generate more heat. Sometimes if we're trying to move either very slow or very fast, and again, these heat dissipation mechanisms are going to have to kick in. What we usually see a lot of times with core temperature is you usually will see a quick increase, and then once we reach a steady state, so a lot of times, especially on a warm day, you'll feel really hot to begin with, because that is actually you getting a big core increase in temperature. But then what happens is those heat dissipation mechanisms start kicking in, and we start dialing in to that level of heat that we're producing, and we match up with the heat we're dissipating, and we stop bringing on any type of core increases. But there is definitely, like I was already saying, a definite role of intensity and to metabolic work, and therefore heat production. Generally, the higher the work rate, and this kind of doing these ones in watts, which if you've ever been someone who's biked a lot of times bike racers tend to use a lot of watt meters, power meters, to determine how hard they're working. Bikes, it's really easy to measure your output, a little bit different than running. But with biking, you can measure the force on those crank arms of the actual pedals, and there's not a loss of force there, so it's very easy for us to kind of say how much power are you doing. And with studies, generally the higher the output of work you're doing, generally the more your core temperature is going to gain. So the higher intensity work you do, generally the more heat production you're going to be doing. There is a pretty wide range that we're okay. So this prescription zone is just kind of saying where we can match up heat production. We can match up our heat dissipation to our heat production. So generally, there's a wide range that we can kind of deal with on this one. But again, the higher and higher intensity we go, and that's what this is showing here. With higher workloads, you have, so this is kind of that steady state. As you get to higher and higher workloads, that zone where you can match these up tends to get smaller and smaller the harder that the higher intensity that you're working. So basically, environmental factors and other things will come into play a lot earlier if you're working at a higher intensity. So higher intensity, higher workloads will cause heat storage earlier on. And again, warmer temperatures are also going to increase the workload. A lot of this has to do is we get more and more heat, we have to start trying to dissipate that heat, and part of doing that is getting blood to the skin. If we're sending blood to the skin, that means at a particular level of output or intensity, that you're likely because you're delivering more blood to the skin, you're delivering less to muscles. So a lot of times this is going to mean with exercise intensity that in a warm environment you're going to start calling on those anaerobic metabolism mechanisms earlier, because again, our delivery of blood and how much oxygen we can pull out of that blood is our VO2 max. If you're sending now, let's say, a quarter of your blood to your skin to cool off versus to your muscles, that is all that oxygen that now is not going to the muscles, which means if you're working at a high enough level of intensity, you're going to start requiring the anaerobic system, and because you can't send as much of your blood or as big a proportion of your blood to those muscles, that means that anaerobic component's going to come in sooner. And this is kind of showing that idea here. Higher temps will increase anaerobic contributions to this. You can kind of see here at these different temps, you can see the shift starts going less aerobic and more anaerobic as temperature increases. And again, this means that your VO2 max in the heat is going to be lower. Again, we're sending blood to the skin, which gets heat to the surface, which can help cool us down. But it also means we have to dilate our blood vessels. It means we're also sending blood to the skin that we're not sending to the muscles, which means less oxygen to the muscles. And less oxygen to the muscle means that muscle cannot do as much work. Because the pressure's lower, we're going to have less preload. We're going to have a lot of times an increase in heart rate to deal with that lower pressure, which all these things are going to make work seem harder in the heat. And because preload is decreasing, it means cardiac output is decreasing. And because VO2 max relies on kind of cardiac output and arteriovenous difference in terms of oxygen, it means also your VO2 max is going to decrease. And this, again, it's kind of saying this here, that decrease in cardiac output means a decrease in VO2 max. And again, this is all going back to the fact that we have more blood going to other areas in a lower blood pressure because of the opening up, the dilating those blood vessels. We're going to have to make the heart work harder, and our stroke volume is going to be decreased. All these things, if we kind of go through all these formulas, we know stroke volume is going to decrease. We know that is part of cardiac output, and we know VO2 max has cardiac output as part of it. So if we decrease this, this decreases, then this subsequently will also decrease. And again, that decrease in flow to these tissues is going to make them slightly more hypoxic, which means more anaerobic metabolism. The other thing it also means is because it takes more oxygen to break down fats, we are going to use carbohydrates at a higher level than we would without the heat, and be preferentially using blood glucose and glycogen relative to fat. So we have decreased fatty acid utilization. Because we're going anaerobic sooner, blood lactate levels are going to increase, and because we can't send blood to things like the liver and the kidneys to help remove this lactate, we are also going to have, we're having increased production of lactate as well as decreased clearance of lactate. So as you're kind of starting to see already, everything when we start putting heat and doing an exercise thing, it is definitely going to have detrimental effects to performance, as we're seeing on almost all these things. These are all adaptations with exercise that we wanted to have happen that made us glycogen spare, not go anaerobic, conserve carbohydrates. And you can see with heat, all that comes in sooner again. So it's kind of like that pre-exercise or pre-adaptation state to exercise. We're kind of going back to that when we start dealing with the heat. We will see on the next set of slides on these, once we get to the next show, that there is adaptations that happen, that about 7 to 14 day time course that will help with this and makes you a little bit better. But the simple sense is, if it's warm enough out, performance is going to decrease. Training and adaptations to heat will make that decrease smaller. but compared to something that is a thermoneutral type of environment, exercise in a thermoneutral type of environment to a hot environment, your performance is always going to be less in that hotter environment, just because we have to send blood to cool the body to the skin. So again, like we're saying here, a lot more glucose from glycogen from the liver, a lot more blood glucose being used, less fats. We start using fast twitch more because there's less oxygen necessary to use those. Again, those create a lot more tension, but they're not going to last as long. So our skeletal muscle contraction starts being less efficient because we're using more and more high energy type of motor units. The other thing is we're going to be breathing at a higher rate, trying to get some of that heat out that way as well. But we don't usually have big changes in the volume, but we are going to increase our respiratory rate. So what we'll look at on the next time here is we'll now take some of this stuff here and start going a little bit more into what are some of the other issues that you deal with exercise in the heat and getting definitely to where this becomes a detriment, and what are some of the kind of more failure state issues that you can have with this. So I will talk to you next time.